Hello, everyone. I'm going to give a brief overview of our work on performance variability and causality in complex systems. This is joint work with Daniel Ratner and Alex Aiken. Complex cyberphysical systems, such as the particle accelerators, contain thousands of sensors that give rise to time series logs, that is, signals. These machines contain diverse heterogeneous subsystems, such as water systems, vacuum gauge, RF cavities, or radio frequency systems that coordinate together to generate a high energy beam. High energy and intensity in beam is essential for various scientific experiments such as crystallography, imaging, and software assessment on hardware chips like CPUs and GPUs. However, often these machines experience performance instabilities caused by various anomalous conditions and subsystem malfunctioning. So in this work, we try to address two questions. First, can we identify degraded performance? Second, can we identify the anomalous subsystems that relate to performance degradation? There is dearth of automated tools in these experimental facilities that can identify the potential causes behind instabilities. Often the domain experts manually examine instabilities using domain knowledge, which is not always efficient, and it is hard to proactively fix subsystems before a subsystem faults or a complete system downtime manifests. So this leads to high human diagnosis efforts and operational costs, and most importantly, wastes expensive machine time. We analyze degraded performance, which is not just failures, that is complete system downtime. For example, in this figure, the first few hours until 3 relates to stable performance. Around 9 hours, we see a short glitch, small glitch, and this is unsteady performance. And around 15 to 18 hours relates to degraded performance, where there is substantial deterioration in the beam quality. So we define performance degradation as increased variability of those signals that indicate overall system performance relative to a reference time of normal behavior. So the idea is to come up with a localized search space containing anomaly-related signals that can guide operators to fix subsystem problems during machine monitoring. There are three main challenges. First is tuning side effects. So many control variables and set points are manually tuned to establish a certain configuration needed for specific experiments. This creates ripple effect. Many other signals get affected, and often there's fluctuation in the performance. So considering both intentional deviations and anomalous deviations, anomaly detection is difficult. Second, correlation is not causation. So for example, in this figure, the RF signal highly correlates with the performance drop as indicated by the energy and intensity signal. However, the actual cause behind this instability is the magnet signal that flips off and on during this anomalous time. So coming up with a list that is short yet accurate is challenging. Also, there are signals that cannot be harnessed with statistical analysis because they are not informative enough, either because they are sparse and irregular or they have low resolution. And finally, even though the machine spreads across multiple kilometers, it's hard to establish an happens before relationship in the signals because there is insignificant propagation delay. So basically, it's a highly dynamical system with many simultaneous events happening concurrently, and we are trying to come up with a short, reduced search space with the anomaly indicative signals. So our approach is to first identify golden signals. The cloud literature refers to golden signals like latency and throughput that indicate system performance. So in our study, pulse energy and transmission intensity are analogous to golden signals. And along with control variables, we try to detect degraded performance and classify the quality of performance as okay, that is steady, or unsteady, or degraded. Next, for an anomalous time window, we do a causal analysis considering the full system scope and also correlate subsystem signal with system performance. So first, we pre-process the identified golden signals and control variables for any given system. Next, we apply prior work on change point detection to find the number of change points in the time window for both the golden signals and the control variables. We come up with a threshold alpha by comparing the number of change points seen during normal times. So the idea is, if the control variables are relatively stable, only then we label the performance. Otherwise, if it is beyond a certain threshold, we ignore because there's a lot of tuning happening in the system. If the number of change points in the golden signals are beyond a certain threshold beta, we label the time window as degraded, else we label it as unsteady. Next, once we have an anomalous time window, we have ground truth for validation that we use for evaluating the results. So the idea is to first look at the correlation coefficient of each signal with performance, beam performance. So we consider both linear and nonlinear correlations using Pearson, Spearman, and Kendall's correlation. Next, as we know, correlation is not causation. So we try to analyze the mean and variance of the signals during various time windows to eliminate those signals that are inherently noisy or are inherently variable because they are not likely to be the cause. Next, we calculate the permutation entropy, which is a variant of Shannon's entropy from information theory. So we split the time window into multiple sub-patterns or ordinal patterns and find the probability distribution across those patterns. The intuition is, if entropy is high, there's more complexity and chaos in the time series. So it's more likely to be indicative of anomaly. Then we analyze the univariate trend in the signal by applying dynamic linear model, which is a form of Kalman filter. It models the latent state space. So the idea is to estimate future states using the known observations until the current state. If there are interesting dips and spikes in the signals, we prioritize those signals over the others. And finally, using all of these metrics, we have a weighted average, which we use as the score, correlation score, to assign the signals. And there are certain regions based on the physical characteristics of the machine that are more likely to be an effect than cause. For example, the regions where the beam is delivered is more likely to be an effect, and the regions where the beam is being generated is more likely to be the cause. So accordingly, we reordered the rank of the signals, if feasible, to obtain the final ranked list. So the operators can look at this kind of a list, and based on the score, we have the rank, and we have the water system, smoke detector, RF, so it speaks of the subsystem, and the physical attributes such as pressure, temperature, current, and also the location like A1, A2. So this way, the operators can look at a certain subsystem with more attention to see if there is something wrong. So overall, our approach can correctly identify performance quality for 86.2 to 92.6% of the cases, out of which less than 17.2% are degraded, 42.6 to 53.4% are unsteady, and the rest are steady, that is okay. We consider two time scales or granularity of the time window to see how our approach evaluates, and the overall detection errors are less than 15%. We assess causality across three systems, all of which are particle accelerators. However, they are not exactly identical in terms of their overall structure and functioning. For LCLS or LS1, we have 52 to 59% of the shortlisted signals as causal. No more than 78% signals are related. So related signals include causal signals along with other signals that may be affected by the cause or that may be in close spatial locality with the cause. For the other two systems, which are storage rings, we have 68.7 to 73.2% of the signals that relate to faulty conditions. We had a limited parameter set for these and could not apply all the steps of causal analysis. But despite that, we have some faulty signals that rank high. And this table shows that each of these steps can help to improve the rank of the causal signal. So for example, for the faulty system is water, subsystem is water, then we can improve the rank from 50 to 2 across correlation coefficient, noise filtering, and calculating the permutation entropy. However, false positives exist. We still have unrelated signals that show up in the top 50 in the ranked list. So we need additional studies, including domain insights, that can help us to improve the confidence of the ranked list. So with this, I would like to summarize and conclude. We studied degraded performance and anomaly localization across a complex set of cyber-physical systems, that is the beam-based experimental facilities. For 86.2 to 92.6% of the times, our approach correctly classifies the performance quality. And we are able to rank the anomaly-related signals amongst the top 1.2% of the considered parameter space. It is feasible to rank anomaly-related signals high enough that can potentially facilitate problem diagnosis for operators during monitoring. Future work entails generalization across diverse anomalous conditions. That includes hyperparameter optimization for different subsystem instabilities, and also including methods that can handle small-scale changes, for example, in the scale of seconds to minutes, and also handling discrete value signals beyond continuous time observations. Thank you, everyone, for listening.